All right, now we're going to go over phase kickback. This isn't an algorithm, but this is an interesting effect that you get by constructing a particular circuit, a little bit like entanglement, that we're going to use as a building block in our next algorithm. All right, so let's just revisit the CNOT once again. When the CNOT has a white ball for control, like in the left column, it does nothing to the target. But when it has a black ball in control on the right, it flips the target. It applies a NOT on the second input. Okay, so the target toggles if and only if the control is black. Control never changes, or does it? This is how we're going to explore the effect of superposition, phase, and entanglement on changing how the CNOT works with our intuition. All right, so let's look at what would happen if we gave a CNOT two inputs in superposition, with the target already having a negative phase, but the control having a positive phase. Okay, so as always, we need to put this in multi-qubit format, and we have a negative phase, so that'll be multiplied along with the rest. So we put the first ball in the first positions, and then the white ball in the first position of the next two. And then we distribute the black balls, and those two have a negative symbol. So the first and third are going to have a negative symbol with the black ball second. And then the second and fourth spot will have that white ball, no negative sign. So now we have four choices, and two of which have a negative sign. We put all of these separately into their own little CNOT, but I do want to note that as we saw in the Fun with Phase video, I have assigned the negative sign to the pair instead of to the individual ball, just so we don't get messed up in remembering that even though we're doing visual representation, that negative sign is going to be associated with the pair. And CNOT doesn't affect the sign. Okay, so let's look at this. Let's put each of these balls through its input of the CNOT, and we can see that in the top two pairs, our control is black, and in the bottom two pairs, the control is white. So we're going to end up swapping those colors on the top two. Okay? So I went ahead and copied over my negative signs for the phase, and I also copied over all of those control bits, because the control doesn't change in an individual CNOT, but the targets do when the controls are black. Okay? So now we have four pairs again, but we'll note they're in a slightly different order this time, which is fine, because remember that while order matters within a pair, the order doesn't matter between pairs. But just so it's easiest for us to put it back into separate bit format, I'm going to just swap the order of those two, so that we have black, 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 white, white, black, black, white, white, so that we can do our opposite tensor product or factor back out into individual bits. Okay. So let's see. Let's figure this out. We have, and the other thing I want to note is that now that negative sign is on a different pair. Okay, it used to be on the black, black, and now it is on the black, white. So let's see how that affects us when we split that back out into the individual pairs. So we still have the same combinations, and so in equal probability. So we know we still have black, white, black, white. The question is, where do the negative signs go? And so what we notice is, well, so these two pairs, there's a negative sign in the bottom pair. And so I'm going to try putting it with the black. And then that would mean that the top pair has one negative sign. The only way the top pair could be positive is if both are negative, because we know that if we multiply -1 times -1, we get +1. So that means that we should try having the black ball on top also be negative, which would cause that second pair to have a negative sign as well. Okay? Now, because those are all the negatives in the puzzle, in the problem, then that means that the two white balls are positive, and everything works out. Okay. What we want to note here is that if you look at our original start and what we got, if you push out all the details and just look at simply the inputs and outputs, what did we get? We got a situation where we used a CNOT and the target did not change, but the control did. This is very interesting, and we are going to exploit this. But we want to notice this, that actually we had the situation where target affected control, and the way it affected the control was by copying the phase from the target to the control. Because if the target, it turns out that if the target had been positive, if everything had been positive, then phase would never have been involved, and the CNOT would have done nothing. So the only time that this changes is when we have this negative phase. Okay, so let's look at what would happen if we put some things around this circuit. So to get to that starting point of the inputs to the CNOT, that would be the same as having H gates. You started out with a white and a black, and you put them through H gates, because black through an H gate turns into the negative phase, and white through an H gate gives you superposition with positive phase. Now we already know what happens when we put these two through the CNOT gate, and so we know that we'll come out with both of these having a negative phase. All right, no problem. Now we put these back through H gates, and look what happened. We get black balls now. So with this circuit, we were able to turn a white ball into a black ball. Even more interestingly, if the second ball had been pure white, then I would never have had a negative phase, and they would both be white on the outside. So this means that we have a way of copying a pure state white or black to another pure state white. Okay. Now make sure, I need to make sure and remind you that it was only because it was a pure state that we were able to do this. So it's not like if I have a superposition, I can copy that, all of the state of that to another qubit. In this case, I'm able to copy the pure state one into the pure state of another using this circuit.